you can go ahead.
Okay, thank you. Okay, good afternoon, everybody. We're the University of Toronto Hyperloop team. My name is Juan. I'm the team captain, and with me is Joe Full. He's the structures lead for the team as well. First of all, I'd like to thank CHC for this opportunity to showcase our work and our progress. And yeah, I'm just gonna let Joe roll with it and continue with the presentation.
Awesome, thanks, Juan. Yeah, so today we're going to be presenting our aerodynamic shell. A lot of people have been involved on this design within UTHT and the University of Toronto, so gladly able to present this and show you what we have been up to. So a quick overview of this presentation. We'll start with the aerodynamics part. We'll go into how we optimized our aerodynamics, what we did specifically for our simulations, as well as the results of those simulations. We'll also go into the material selection for the pod, as well as the structural simulations that went along with those. And then lastly, we'll take you into our manufacturing process, which is currently still in progress. So that's kind of exciting there. So starting off with the aerodynamic optimization, how we first started conceptualizing different geometries of our pod was based on other high-speed transportations, namely like airplanes. So we have an airplane nose design that we iterated through, an airfoil design, and then a bullet design, which is pretty common with these high-speed trains. It's similar to the one that Virgin Hyperloop is currently developing. So we just did a simple CFD analysis using ANSYS CFX solver and evaluated their performance against the maximum pressure as well as the maximum turbulent kinetic energy, with the higher importance being on the pressure. So trying to limit the amount of pressure that our pod is feeling in order to optimize the aerodynamics, the speed, as well as structural considerations as well. So here's just a quick background on our boundary conditions and our settings. So we used a K epsilon model and set our inlet velocity to 70 meters per second, which is roughly, I think, 250 kilometers an hour, which is our anticipated top speed from our MRAX motor, which is anticipated for a kilometer truck. Then the pressure is 0.001 atmospheres, which is the minimum pressure limit inside the CHC tube, and the temperature being 28 degrees, as well as some residual settings and number of iterations based on research that we've done on this as well. So from that, these were our results. So the top figure here shows the velocity contour, and the bottom figure shows the pressure contour. So from the velocity contour, we can see that the largest air velocity is at the top of the pod, as you can see in the red color. This provides a desired downforce, which allows us to propel as well. And then at the back of the pod, we kind of get an interesting effect. If you see the bluish at the back and the green, it provides a little bit of a small thrust that actually goes forward, which is an aerodynamic feature that you see a lot in cars, but it's insignificant for a smaller scale pod. If we were to build a larger scale pod, then this angle is more looked into. But it's quite interesting that we were able to still find this desired aerodynamic effect. Then for the pressure contour, as you can see at the nose of the pod, right at the front, we have a very red concentrated area there, which is as expected. We expected most of the pressure to be at the nose of the pod. So in future iterations, maybe we can redesign that to kind of distribute this pressure better. But these were our results. And one thing I like to note is you see this long tube. So we have about 2 to 3 meters on either side, the front and the back of the pod, which allows for a nice flow to be simulated in ANSYS itself. So that's it for the aerodynamics and CFD section, and the next section leads into the material selection. So our objective for this, the shell itself, was to minimize the mass, as a lighter structure will allow the pod to accelerate faster. And the constraint we put on our design was to minimize the deflection during the pod's operation. The reason for this is because if you're having a lot of deflection happen on your pod during the actual run, you're actually going to affect your aerodynamics. And we also don't want any deformation or failure to happen in the pod itself. So it's paramount to design for the deflection as well. So we have our objective equation, which is just a mass equation, just using density times volume, and then our constraint equation, which is deflection using some force divided by mainly geometric pattern considerations over there. So from this, we get our materials performance index, which is based on the Young's modulus, E, as well as rho, which is the density. So from this, we were able to come up with some nice graphs, which are shown on the next slide. And as you can see, we have our density on our y-axis and a Young modulus on our x-axis, with this slope being 3, I believe, which comes from our MPI equation right here. Sorry, the slope is going to be a third. So we want to maximize this. So we want to have low density as possible with the highest Young's modulus. So we plot our line over here, and then we take all the lines on, or all the materials on the right hand of the graph. From this, we got 5 main materials. As you can see, there's a lot of grayed out materials as well. Those were materials that we filtered out. CES, or Cambridge Engineering Selector, is a huge software where you can select different materials. It has all their properties as well. So one thing we did was minimize or limit this to only composite materials, because metals and ceramics are going to be too hard to get something in an organic shape, as well as ceramics probably being too brittle to use for this design. So from this, we got our best material as a woven prepreg, which is pre-impregnated carbon fiber. And essentially that's carbon fiber with epoxy already impregnated in it. So you just lay it up, you heat it in an autoclave, and then you get your nice part over there. So next we'll go into the structural simulations, and we'll talk more about the materials and how they were used in the actual manufacturing method. So we did a simple structural simulation of just putting the pressure from the aerodynamic simulations, the maximum pressure being just over 3,000 pascals. And we distribute that all along the face of the pod. And then we fix the pod in these green highlighted areas. And I'll show what that means in the next slide. So those green highlighted areas represent L brackets, which are epoxy to the shell. So you can see in the figure on the right, there are 8 different L brackets, which are currently bolted to our frame. And then those will be epoxy to the shell, as you can see in the image on the left. And those will fix the shell to the pod. So those will be the fixture points. Then the next shows the structural simulations for our composite analysis. So because we're using pre-impregnated carbon fiber, there's considerations to how you actually lay those up and the orientations of the fibers. So what we did is, you don't just use one layer of pre-preg carbon fiber, you usually use multiple of them. We decided to test 2 different ones as well as 3 different ones. So iterations 1 to 3 go through 2 layers, where iterations 4 to 9 go through 3 layers. So we looked at different angles, namely those ones that are nice angles, so 0, 45 degrees, 90 degrees, and stacking them up against each other. Again, when I show the manufacturing, this will kind of make a little bit more sense. But as you can see in the last 2 columns, we have our maximum deformation and maximum stress, which shows how much the actual orientation matters. So for example, for 6, our best iteration in terms of maximum deformation, we only had 0.3 millimeters, whereas iteration number 4, that also has 3 layers, has maximum deformation of 0.45 millimeters, which is noticeably different. So you can see how optimizing the actual orientation of how these pre-preg layers stack up is important in the design. So now we'll jump into how we're actually manufacturing, and we can kind of take you through what we've done so far and what we plan to do in the near future preparing for CHC. So we started with our male mold, or our male plug, which essentially is just pieces of foam that we CNC'd along the pod. So as you can see on the picture on the left, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think, sections that are then cut in half as well. So we have all our foam, which we essentially just epoxy those together, and then we wrap them up in fiberglass, and that's shown in the picture on the right. It's all wrapped up in fiberglass. So this was the start of our mold, and then we continued to work on that. So we had to basically fill with something known as Bondo, or auto body filler, which essentially is used to perfect the shape of our geometry. We want it to be as perfect as possible, as smooth as possible with no bumps. So we went with our Bondo, put all that in to get rid of bumps, and then we prime it with this black paint right here, which is shown in the middle. And that process is repeated roughly 10 times. I think it's probably been more than 10 times now. Basically trying to get the pod as smooth as possible, the curvature as nice as possible. So when we do our other steps, everything shows up well. So our next step is the female mold. So we're basically just finishing up the male mold right now. And then we go into the female mold, which is going to be into 2 halves. So as you can see on the picture on the right, we have this blue line which intersects the pod longitudinally in half. And essentially we'll make 2 halves of our female mold using what's known as the vacuum infusion process, which essentially consists of putting some piece of fiberglass on top of your female or your male mold, and then putting a vacuum bag over that, and then injecting your epoxy in there. And then you basically just put that in a vacuum to have the bag cured to the side of the pod, and then you have your nice mold over there. So we'll have 2 halves of our mold, which will then get joined together, and then we can start laying up our final part. So this is what we adopted here, which is a sandwich structure, which essentially reduces the density but keeps the strength and integrity of our pod as well. So we have at the top 3 layers of pre-preg carbon fiber. In the middle, we have our Nomex honeycomb core, which is very low density, and 3 more layers of pre-preg carbon fiber at the bottom. So essentially what we're going to do is take our female mold and lay up the 3 pieces of carbon fiber in the orientation that we selected, put honeycomb on that, and then 3 more layers. And then from that, we're going to put our pod in autoclave, let it cure, and then we have our final part. Our final part is actually cut into 2 sections. I don't know if we have a picture that shows that. I guess you can kind of see in this picture. There's this line in the middle of a pod. So our pod is actually in 2 pieces. And the reason for that is because our shell wraps around greater than 180 degrees. So to take it out of a mold would be virtually impossible if it was a single piece. You'd either damage your part or damage your mold. So we'd have to do our pod into 2 different halves that way. And then those have a lip that allows them to connect to each other. And then when they're bolted to the actual frame, the space between those lips will be virtually 0. So that's how we make sure those pieces are stuck together. And then our last part would be to surface finish this pod. So sand it and then paint it and then make it look nice and pretty. Have all our sponsors here as well. And yeah, that's pretty much where we're at with our aero shell. We'd like to just invite you to answer any question or ask any questions.
Hi, I might have a question for you, Jovan.
Yep.
Well, first of all, a nice presentation. Do you have an idea of the cost structure?
Sorry, you cut out there. I think you're asking about the cost of everything.
Yes, well, of the shell.
Yeah, so can't get into too many specifics here, but this honeycomb piece right here is fairly inexpensive, and the actual pre-preg itself is probably the most expensive. So I think were on the order of magnitude around $1,000 for the material for the shell.
Hello. What is the purpose of the honeycomb core in your shell design? And do you see any types of challenges when it comes to actually laying up such a core, given that it's generally not, it's quite stiff and it would be difficult to, at least in my eyes, conform to the curvature of your shell? So have there been any challenges addressed or foreseen with that?
Yeah, that's a good question. A lot of people have the conception that the honeycomb is actually stiff, but it's actually quite elastic in nature. I mean, when they sent it to us, it was like packaged up in a roll. So it's quite flexible and it can adhere to the curvature of the shell. The reason we have it is, I can go back to our material selection here. So if we go back to this slide over here, if we were to incorporate something with the honeycomb structure in here, essentially what we're doing is we're lowering the density. Although our stiffness or Young's modulus might be decreased, we're lowering the density such that that material will lie on the right side of the line. I don't know if that answers your question. I can try to give a better explanation if you need.
Is it, so have you considered not like, so if you were to just not include it at all, what is the concern if you were to just lay up several sheets of carbon on their own rather than having the honeycomb in the mix?
So you would need a thicker, like you would need more layers. We only have 3 on each side, so that's 6 total layers. If we weren't to include the honeycomb, we would need, I don't know how many layers off the top of my head, but it would be more layers to achieve the same amount of performance. So adding in the honeycomb just increases the efficiency of not increasing the density and also not increasing the cost too much.
But if you know, if you're only if there are only certain parts of the shell that need to provide some sort of structural stiffness to house the, or I guess connect to the your drivetrain and your mechanical components, is there a need to structurally support the entire pod? So if there's just areas that are going to be essentially just a shell and not necessarily supporting anything.
Yeah, that's a good point to bring up. I mean, it's probably something to look forward to the next part, but I think if we just incorporate the honeycomb in certain parts of the pod, it would provide a lot of manufacturing difficulties. But I can show you, where is this? To address that concern of adding extra support, I didn't mention this in the presentation, but this, sorry, going too far. This figure right here, if you can see the blue pieces, those are pieces of foam, which allow the frame or this black carbon fiber tubes here to connect to our shell or hold them. That provides one dampening, and also like at the top, we might have a crash or something happen. So we have that extra foam that helps out.
I was just going to say, if you had looked into like a like a Divini cell foam, if you ever heard of that, it's kind of like a polystyrene that kind of provides the same types of structural stability that I guess you're looking for with the honeycomb, but at a reduced weight and thickness. Oh, just a question. So sorry, with the six layers of carbon fiber is actually a fair amount given the scale of your vehicle. is that not enough to meet your structural needs, I guess? Or?
Yeah, in honesty, the 6 layers would most likely be enough. But just to get it a little more thick and not leave it too brittle, because carbon fiber can be brittle, that's another reason why we chose to incorporate a honeycomb in there.
Great, thank you.
No problem.
Are there any more questions from the participants? Cannot see anything in the chat. We can just wait a couple more seconds, and thank you for your presentation, UTHT. Good work, and I think it's just.
I have another question. Is the I couldn't just remember, but is the mold release going to be along that release line you showed at the end, in the middle of the pod, or is it along like the longitudinal axis of the shell?
You're muted, Joan.
Joanne, I think we can't hear you.
Not yet. You're still muted. There you are.
Yeah. Okay. Sorry. Yeah. So it is cut in the longitudinal axis for our female mold, and then the actual part is cut at that thick black line. That's the 2 halves of our final part.
So okay. So is that so? Do you see it being easier to release the mold along that axis compared to, I guess, if you were to, because I'm guessing like you'll have like a left and a right side of the mold, right?
Yeah.
Is that easier than having like a top and bottom, just because of how like deep you would be having the male plug?
Yeah, exactly. So how we'd actually do this is we'd lay up 1/2, like the front half, for example, along the female mold, and then the other half will be laid up on the other side, and then we can easily take the mold off from those 2 sides.
Okay, I guess then Peter's done with his questions, and thank you again. Thank you for the presentation. So I guess UTHT's presentation was the last one. So I'm just going to take the screen control from you to go over what we'll have tomorrow.
Yep, no problem.
So thank you once again for all the teams who came today. It was really good to listen to your presentations, to learn a lot from what your team has been working on for the past few months or years. So it was it's the first time for CHC, and as a team, we are really happy that you all could make it up to the presentation, and we thank you for that. So tomorrow, the rest of the teams will continue. So we'll start at 11. And we have Queens. Queens talking about propulsion and levitation project, followed by Cooper Loop, mechanical side, and then it's Ryerson and Wester. And then we have like the closing ceremony, which will, so the presentations will all end at 2 p.m. tomorrow. And for those who are interested, today Waterloop, I think it was at 4 p.m. that they started their Goose 5 pod unveil. And you can click this link. I think it's supposed to be an L here. So wloop.ca /pod unveil. So you can go there and watch them unveil their Goose 5 pod for those of you who are interested. And then, yeah, thank you once again for everyone who came. It was really good.